So here's where we left off yesterday, if you weren't in class. Yesterday we talked about the Earth as it compares to the solar system and kind of some characteristics about our solar system. But today we are going to talk about kind of what's beyond the solar system in very simple terms. We're not going to get way out there and talking about some of this stuff, because if you want to, you can get there, right? But we're going to keep it real simple. So again, our solar system is the sun and everything that orbits around it. So planets, asteroids, comets, the moons of all the planets, all those things make up our solar system. But today we're going to talk about, again, what's past that, or what's beyond our solar system. So back and that. There we go. All right, so we have our solar system, which is the cluster of things that orbit around our sun, but the Milky Way galaxy. So a galaxy is kind of the next biggest classification, right? So we're in space, but we're trying to organize things just like we would if we were talking about things very small, right? When we talk about an atom and what makes up an atom, and then we go bigger and bigger and bigger. Same thing with space. We kind of categorize things until we get into such a big unknown that it can no longer be categorized, right? So we have our Earth, and then the solar system, and now the galaxy. So the galaxy is a huge group of stars, anywhere from 1 million to 1 trillion, somewhere in there, right? So this giant number of stars that are kind of clustered together. And essentially, surprise, surprise, held together by gravity, right? So gravity kind of orients all these things together, just like the planets in our solar system are held together by the gravity of the sun. So the galaxy, the Milky Way galaxy, right? You've probably heard that name, is kind of also held together by gravity. So our solar system is just one single star out of all these millions or billions or trillions of stars that make up the Milky Way galaxy. And the Milky Way galaxy, you've maybe seen pictures of, it's seen like that kind of spiral shape of stars. That's kind of a visual representation of what the Milky Way kind of looks like. So maybe you've even seen on really bright dark nights, when the stars are especially bright, you can look up and you can kind of see a band of stars. You're essentially seeing a portion of that spiral of our galaxy, right, of the Milky Way galaxy. Okay? And again, galaxies are large groups of stars and clouds of gas and dust that are held together by gravity. All right? So the bulk of kind of what we'll talk about today is just kind of what is a star and kind of the life cycle of kind of how a star is born and then how it dies. It's not really a living thing per se, but it still has a finite life. So stars are basically globes or balls of hydrogen and helium gas that produce their own heat and light through constant nuclear reactions. So you don't need to fully grasp that, but just kind of keep in mind that a star is basically a ball of gas that's constantly undergoing heat reaction. So that's why they glow, and that's why they emit so much heat and light, right? But anything that is emitting that much energy, in terms of light energy, heat energy, anything that's doing that is going to have a finite lifespan. It cannot do that forever, right? That's the amount of energy put into generating the heat and light that a star puts out, like our sun, right? That's an immense amount of energy, and eventually it will run out of energy, right? And so that's kind of what we're going to talk about today. So the life cycle of a star, in very basic terms, is about 10 billion years long, okay? So when we say it's finite, It is, but it's also extremely long in terms of relative to human life, right? So 10 billion years is a long time. Stars begin as what we call protostars. In other words, they're kind of the beginnings of a star. And they are formed by clouds of condensing gases and dust called nebulae. So what happens in our solar system is once a cluster of gas or dust starts to collect, it builds on itself because of the forces of gravity. So in totally blank, empty space, there is no gravity to speak of. When particles collide, you start to get a small cluster of gas and dust. And as that builds, the gravity of that object becomes greater and greater, and it collects more and more, and it collects more and more, and it just keeps going and going and going, right? And that's how you end up getting a little cluster of that gas and dust that ends up being a big cluster of gas and dust and becomes a star. Okay? So, long story short, those protostars gain enough power and enough energy where they eventually become a star. And when we think of kind of the typical star, we're referring to what we call a main sequence star. And that's basically the adult lifespan. If you want to compare it to animals or like life as we think of it, right? The main sequence star is basically a fully developed star, right? And that's its main or its kind of adult, like I said. And that's the longest stage of a star's life. So the majority of that 10 billion years in a star's lifetime from beginning to end, the majority of that 10 billion years is spent as a main sequence star. So our sun is a main sequence star, somewhere in the middle of that 10 billion years. It's not young, it's not old. After billions of years, that star slowly begins to run out of hydrogen fuel. And so, because it's running out of fuel and those reactions are slowing down, two things happen. One, it changes color. So it goes from kind of a white or yellowish color, which we associate with extreme heat, and it actually begins to turn red. And that's because it's starting to cool down, losing its heat energy. And it's also becoming bigger because the reactions aren't happening as frequently. And the reactions are what kind of keeps the star a constant shape, or not shape, a constant size, or constant mass. But when the reactions slow down, the mass of the star actually builds and builds and builds, and it becomes bigger and bigger and bigger. Okay? So what we get is kind of a dying star or an older star, and we call these red giants. And so we know of a few of these red giants that you can look at and see, and they look red. And that's because they're emitting less light and heat energy. And they're also very, very big, which is part of why, even though they're emitting less light energy, you can still see them. So eventually, that red giant starts to become unstable. And so, meaning it's starting to reach the end point of its life. And stars can die or collapse in a couple different ways. So first, and the most kind of dramatic, is an explosion called a supernova. So a supernova is where that red giant becomes so unstable that something happens and it explodes, right? And what's left behind is what's called a neutron star. And again, don't panic. You don't have to memorize all this stuff. I'm just kind of giving you the basic details, and then we'll go from there, right? But so you have this supernova, which is a big star exploding, and you have this little neutron star behind, and it just kind of peters out, becoming a white dwarf star, which, again, all of these are just fancy terms for we have a star, gets bigger and loses its energy, explodes, and what's left is this little tiny star that kind of dies out slowly. right? Now, down here on the very bottom, it says neutron stars can be very dense. So the reason for that is if you have a giant star that explodes, what's left, even though it can be tiny, can be extremely dense compared to the star when it was in its normal lifespan. That can make gravity do some crazy things. And that is how you end up with black holes. And we are not, for those of you very interested in black holes, we're not going to go down that path because first of all, I don't know enough about them. Secondly, you don't need to know anything about them. You need to know anything. We don't need to be black hole experts to pass the GED. Right? Black holes are interesting, and there's things we don't know much about. But if you want someone to elaborate on black holes, Alex is your man at YouthBuild. You can talk black holes for days, right? But essentially how they're formed is what's left of these dead stars is this tiny, tiny, dense ball. And it can be so dense that it causes gravity to actually collapse in on itself, right? And that makes a black hole. And we call them black holes because the gravity in them is so strong and so great, light doesn't escape from them. And so you can't compute that, you're not alone. That is crazy talk, right? But that's essentially where that term comes from. You look at, if you can see a black hole in space, it literally looks like an empty, vacant black spot, right? No light coming through. So again, black holes are a topic for another day, but that's kind of the general lifespan of a star. Okay? So 10 billion years, protostar, main sequence star, red giant, supernova. All right, so let's see. We've got plenty of time. I've got one more group of questions to do, and then we are done with Earth and space science, except for a little review tomorrow. So again, if you joined us late, tomorrow we will review all of the Earth and space science we've gone over the last week or week and a half. And then Monday we will start on a brand new topic. So let me pull up the practice questions. And I don't actually know if I have gone through these. These might be new practice questions for whatever reason. They don't look familiar. So we're kind of in this together. So let me pull up this. So the first three questions all deal with this paragraph and the chart. So I'll zoom in on the paragraph and the chart so we can kind of try to see it clearly. And then we'll go through the questions kind of one by one. So it says, in astronomy, magnitude is an indication of the brightness of a celestial body. In other words, how bright a star. Magnitudes are measured along a scale from positive to 0 to negative, with brightness increasing as magnitude increases. So the greater the magnitude, the brighter it is. Magnitude is categorized two ways. Apparent magnitude is the brightness as seen from Earth, either by the naked eye or photographic. So when we look out and we see a star, apparent magnitude is how bright does it look to us. All right. Absolute magnitude, however, is a measure of the actual brightness of an object. So in other words, it doesn't take into account how bright it looks from Earth. It just says how bright is it compared to other stars. And the way that they define that is by this last sentence. It says, it is defined as the apparent magnitude of the object, the apparent magnitude the object would have if it were located 32.6 light years from Earth. Because in general, of course, size and the amount of light energy that a star puts out factor into how bright it looks from Earth, but so does how far away from Earth. So whereas apparent magnitude just says how bright something is from Earth, absolute magnitude says if distance were equal. In other words, if all stars were the equal distance away from Earth, then how bright would they really be, right? That's the difference. So hopefully you can parse together what I'm getting at. I don't even know why it doesn't make any sense. All right, but hopefully you understand what I'm saying. So this chart is of the 5 brightest stars that we know. We have the star name, the distance from Earth in light years, the apparent magnitude, and the absolute magnitude. Okay. Sirius, 8.7 light years from Earth. It has a negative 1.47 apparent magnitude and a plus 1.41 absolute magnitude. And then we have all these other various ones. So I'm not going to go through it. Just want you to all see. We have Canopus. I think I'm pronouncing these. Actually, I don't know if I'm pronouncing them right or not. Canopus, Alpha Centauri, Arcturus, and Vega. And those are the 5 brightest stars we have. So, with that said, let's look at number 1. Number 1 says, choose information from the chart below to fill in the blanks. As seen from Earth, blank is the brightest star. However, if all the stars listed in the chart were 32.6 light years from Earth, then blank would be the brightest star. Okay, so think about kind of what that's asking us, and then I'm going to answers and make sure I don't make a fool of myself. All right. So the confusing thing here is we need to make sure we read this carefully. Okay, and what I mean by that is it says if we read the thing about magnitudes, it says magnitudes are measured along a scale from positive to 0 to negative, with brightness increasing as magnitude increases. Or sorry, brightness increasing as magnitude decreases. So what that means is negative values are brighter than positive values. So it's kind of weird to think about and easily confused. You can be easily confused by that. So in other words, we're looking for negative values to represent the brightest stars. So as seen from Earth, sorry, that tangent, I just wanted to make sure we're clear on that because that's pretty confusing. Brightness increases as magnitude decreases. So we've got all these values here. Apparent magnitude is, again, how bright something is as it's seen from Earth. So which would be the brightest star seen from Earth, which is the first fill in the blank. And again, we're looking for the highest negative value. Okay? Negative 1.47, negative 0.71, negative 0.1, negative 0.06, and positive 0.03. So Sirius at negative 1.47 is the brightest star seen from Earth. In other words, if you take away distance, if you're not concerned with distance, right? Sirius is the brightest star that we see. Okay? But if all the stars listed in the chart were the same distance away, 32.6 light years from Earth, then blank would be the brightest. So what that's asking us is, according to absolute magnitude, what is really the brightest star? And it's not even close, right? By far, Canopus at negative 4.7 is the brightest star that we know of, that we've discovered, right? And notice that makes sense because it's still the second brightest star as seen from Earth, and it's 180 light years away compared to all of these others. Sirius, 8.7, Alpha Centauri, 4.3, so that's the closest star. Arcturus and Vega. They're all way closer than Canopus. It's still the second brightest star. So it makes sense that if you held distance constant, in other words, that you considered them all to be the same, Canopus would be the brightest. So there's your answer. Sirius, number 1, and number 2 would be cannibals. All right, so let's look at number 2. Make sure I'm doing okay on time. All right, so number 2, sorry, I'm zooming out. I'm going to make sure we are being able to see the chart. So number 2 says, for those of you that can't read it or want me to read it to you, 2 says, which of the following would be true of a star with a position 32.6 light years from Earth? The star's absolute magnitude would be less than that of Alpha Centauri. The star's apparent magnitude would be greater than its absolute magnitude. The star's apparent magnitude would be equal to its absolute magnitude, and the star's apparent magnitude would be greater than that of Arcturus. All right, so these weird names make it seem like even maybe a more confusing question than the past. So the key here is, do you understand the difference between apparent magnitude and absolute magnitude? And again, here's an example of a concept that until we read this, we had never heard about this. So it's something unfamiliar to you. And to me as well, right? I'm in the same boat, right? But that doesn't mean you can't answer the question. We just need to make sure we know what it is that they're talking about and how we can best find the answer. So we know apparent magnitude is how bright something is from Earth. Absolute magnitude is how bright something would be from Earth if it were 32.67. Okay? So what this question's asking us is, if a star was actually exactly 32.6 light years away from Earth, what would be true? Well, the first 2 that I'd throw out right away are A and D. The star's absolute magnitude would be less than that of Alpha Centauri, and D, the star's apparent magnitude would be greater than that of Arcturus. Okay? I would focus on B and C. The star's apparent magnitude would be greater than its absolute magnitude, or C, the star's apparent magnitude would be equal to its absolute magnitude. So what do you think? Again, remember, apparent is what it looks like from Earth. Absolute is what it looks like from Earth if it were 32 light years away. So in this situation, if there was a star that was exactly that distance away, guess what? 2 would be equal. So the right answer here is C. The star's apparent magnitude would be equal to its absolute magnitude. Okay? And then let's look at the last question. So the last question here is number 3. Or sorry, the last question dealing with this chart in the graph, or the chart in the paragraph. Number 3 says, a magazine article makes the following statement about stars. A star's apparent magnitude and its absolute magnitude must always be close in value. Which of the following explains why the magazine's statement is incorrect? We know from looking at this chart, we can see lots of stars where the apparent magnitude and absolute magnitude is very different. Canopus, the difference is huge, and Alpha Centauri, the distance is huge. So which of the following explains why that statement is false? A, stars form from huge masses of dust and gas. B, the absolute magnitude of a star indicates how bright the star looks to viewers on Earth. C, the apparent magnitude of a star is a measure of the amount of light the star puts out. Or D, not all stars are located about 32.6 light years from Earth. Okay? So if we weed through these, what makes the most sense? Why is that statement false? Okay? First, A and B are simply facts. Stars form from huge masses of dust and gas. Great, we know that. That doesn't explain why apparent and absolute magnitude can be different. Same thing with B. B just tells you what absolute magnitude is. Again, or actually, it doesn't even do that. If you read B carefully, the absolute magnitude of a star indicates how bright the star looks to viewers on Earth. That's actually defining what apparent magnitude is. So first of all, it's fact and it's false fact. It's falsely stated, right? So let's look at C and D. C says the apparent magnitude of a star is a measure of the amount of light the star puts out. That's not true. The apparent magnitude is just how bright something looks from Earth. It doesn't. So B and C are like flip-flop. B is describing apparent magnitude, C is describing absolute magnitude, but they've flipped them around. So A is a true statement. B and C are just false statements. And so by default, D is going to be the right answer, but let's see. It says not all stars are located about 32 light years from Earth. Right? No brainer, right? That's the reason why, if you look at the chart, Canopus is way brighter in reality than it appears on Earth because it's so far away. Same with Alpha Centauri. It is much brighter from Earth than it really is relative to other stars because it's so close. That makes sense, okay? Or at least, hopefully. Okay, so let's look at these last two. They deal with something completely different. Hopefully you can still see that. So number 4 talks about our sun. And it says, the sun is about 4.7 billion years old, based on the information on the page prior. So we don't really even need to go back because just the same information that we were talking about earlier. At which stage of its life cycle is our sun? A protostar, B, a main sequence star, C, a neutron star, or D, a white dwarf. So remember, we talked about stars' lifetimes being about 10 billion years. And they spend so the sun is 4.7 billion, almost right in the middle, right? So where does a star spend the majority of its lifetime? B, a main sequence star. So that one's pretty easy. Now let's look at number 5. Number 5 talks about Pluto. So it says Pluto has a diameter of just 1,438 miles. It is made mostly of ice and frozen rock. It is very small and has an irregular orbit. It was originally classified as the 9th planet from the Sun, but it has since been recategorized as a dwarf planet within the Kuiper Belt. Which of the following is not factual detail about Pluto? Okay? So we're looking for which of these 4 statements is not a factual detail. A, Pluto has a diameter of 1,438 miles. B, Pluto is made mostly of ice and frozen rock. C, Pluto has an irregular orbit. Or D, Pluto should be classified as a dwarf planet. Just the way that these 4 options are worded should give it away. But Pluto has a diameter of 1,438 feet. That is a factual detail. Right? B, it is made of ice and frozen rock. Factual detail. C, it has an irregular orbit. Factual detail. Pluto should be classified as a dwarf planet. The fact they use the word should be a red flag that is implying it's not a fact. It's saying Pluto should be something. Right? So D is the right answer here. Hopefully I didn't go through those last two too quickly. But yeah, sometimes the right answer just pops out at you and you don't need to spend a lot of time on it. All right, so 1:45 on the nose. We'll go ahead and stop there for the day. Hopefully these Earth and space lessons have been helpful. Tomorrow, again, we'll review this section, and then Monday we will start talking about biology and some life science stuff. Spend a week or 2 going through that. That's all I've got for today. So hopefully I will see everybody virtually back here tomorrow. And with that, I will leave you be for the rest of the day. Hope everybody has a nice rest of your day, and I will talk to you next time.